Wastewater from industrial metal finishing contains hexavalent chromium, a highly toxic compound. Before this water can be safely discharged into the environment, treatment plants must chemically reduce the chromium from its toxic hexavalent state down to a safer trivalent state. This NMFRC text mandates an effluent concentration under 0.1 milligrams per liter of hexavalent chromium. It outlines sodium metabisulphite as the reagent of choice. Crucially, this reduction is highly dependent on an acidic environment, requiring operators to lower wastewater pH between 2.0 and 3.0. Because the discharge limits are so tightly regulated, operators cannot rely on guesswork. Finding the exact dose of sodium metabisulphite required for the reduction process is a strict legal necessity to keep the plant in compliance. To determine that exact dose, operators run a bench scale jar test. This involves adding different amounts of sodium metabisulphite to several sample jars of wastewater to find the precise chemical amount required to complete the reaction. You can't visually confirm when chromium is fully reduced, so operators use an oxidation reduction potential, or ORP, meter. This Yokogawa electric chart shows acceptable ORP ranges. Operators inject chemical until the meter hits approximately 280 millivolts, indicating successful hexavalent chromium reduction. In the jar test, the operator checks multiple samples, finding the single jar that reaches this 280 millivolt target using the lowest possible amount. That winning jar gives us our optimal target dose. For our calculations, let's say the ideal concentration is 15 milligrams per liter of wastewater. We will use this number to scale up to full plant operations. But there is a practical problem in the lab. Measuring exactly 15 milligrams of dry powder into a single 1-liter jar requires extremely sensitive and expensive equipment. To solve this, we make a liquid stock solution. First, we confirm our material. This safety data sheet identifies sodium metabisulphite with the CAS number 768157-4 and a molecular weight of 190.11. Next, we use a standard lab technique. By dissolving exactly 1 gram of the dry chemical into 1 liter of distilled water, we create a 0.1% weight by volume stock solution. This specific concentration creates a perfect 1-to-1 ratio for testing. Adding 1 milliliter of this liquid stock solution to a 1-liter sample of wastewater delivers a dose of exactly 1 milligram per liter. This ratio eliminates the need for complex conversions at the bench. If our target dose is 15 milligrams per liter, the operator simply uses a standard pipette to add 15 milliliters of the stock solution to the jar. Once the lab confirms that 15 milligrams per liter works, we have to translate that small-scale target into a daily feed rate for the entire treatment plant. To do this, operators use the industry-standard pounds formula. The feed rate in pounds per day equals the target dosage in milligrams per liter, multiplied by the daily flow in million gallons per day, multiplied by the conversion factor of 8.34. However, pure mathematics often collide with physical reality. As noted in this reference document, actual chemical dosages required in the field are frequently much higher than theoretical calculations due to impurities in the commercial chemical and reaction inefficiencies. To account for this, we adjust the pounds formula by dividing the entire equation by the decimal purity or efficiency factor of the specific sodium metabisulphite product being used at the plant. Let's put this into practice. We have our lab-tested dose of 15 milligrams per liter and a plant flow of 1.5 million gallons per day. If our commercial sodium metabisulphite solution has an active purity of 50%, we divide by 0.50. Omitting this final step is a critical error. Without the purity adjustment, the plant would dose only half the necessary chemical, leading to an incomplete reaction and heavy fines for discharging toxic chromium. Running those numbers gives us a final feed rate of 375.3 pounds per day. The operator can now dial this precise value into the chemical feed pump to maintain compliance. Before handling these large quantities on the plant floor, operators must review the safety data sheet. Section 8 details the required personal protective equipment, specifically mandating nitrile rubber gloves and approved eye and face protection to prevent severe chemical burns. By combining bench-scale accuracy with rigorous plant-scale math, operators take control of the treatment process. Using the 1-to-1 stock solution rule in the lab provides a reliable target dose, and adjusting the pounds formula for purity ensures that exact dose is delivered in the field. When every calculation is correct, precision dosing ensures complete environmental compliance.